In the earlier 2 weeks, we actually review all the necessary discrete math, including propositions, predicates, sets, relations, and also functions. So these are the important concepts in order for you to really write formal specifications in terms of mathematics. That's something we'll definitely see as we go for our first case study. So there will be a number of case studies we would like to do throughout the course, but the first one is going to be talked about in the most details. We want to go slowly, and for the first one, it's going to be a big one. So if you look into the corresponding chapter number 2 of the modeling in event B, that one is almost 80 pages. So I want to go very slowly with you about every detail of the model and also the proving process whenever possible. And we're going to spend about hopefully between 3 and 4 weeks to really finish this case study before the reading week. That's my hope. But if it has to be shorter, it has to be longer, we'll see how that goes. But just enjoy the learning about formally specifying and refining a system. And the first category of system that we're going to speak about is a reactive system, where you got sensors and actuators to really get connected and control the physical environments that you actually work in. And specifically, we want to consider a bridge controller, which will regulate how cars can actually go between the mainland and also some island using a bridge. That's something I'll give you more details as I talk about the requirements documents. All right, so that's a very brief introduction and put into context about what we're going to do in the coming at least 4 weeks. And we're going to focus on this particular case study. And the lecture itself is going to focus more on the theory and also exercises on the paper or the slides. If there's any time allowed, I will definitely try to see if I can put something on the rodent and to show to you some insight. Otherwise, I can leave that to the lab exercises or some extra ones for you to do. All right, let's now talk about it. And as usual, let's talk about what we expect you to really learn by finishing this long module. It's going to take a long time to really make sure you properly learn it. But ultimately, we want you to understand, number one, about what a requirements document is. Specifically, this week, we'll actually make sure we mention about the entire requirements document for. Think about requirements document always consists of 2 parts. One is about assumptions about the working environments, and the other one is about the intended functionality that you want the working system to really satisfy. So these are the 2 things you always want to address in the requirements document. But for this course, we will always give you the requirements documents that's actually written in English. But to really formalize what's really said in the requirements documents, either the E description or R description. In that case, the formalization process will be your responsibility as an engineer, as an assistant architect. And what a refinement is, we'll definitely see 3 refinement steps as we construct the models, right? So in total, we're going to see 4 different models for this bridge controller as we'll go. And for each refinements, we're going to introduce just a little more details to really prove some additional properties. That's something we'll see as we go. And we're going to learn about how to write formal specification using what you actually got reviewed from the earlier 2 weeks, using predicates, propositions, sets, relations, and functions, and etc. And in Rodent, the tool, if you hopefully you already completed lab number 1 tutorial, which you are supposed to. So there are 2 kinds of formal specification you can write in Rodent. One would be the so-called static context, meaning that they don't really change. They don't really change as events occur in the system. They always remain constant. They always remain static. That will include constants and also axiom, for example, the typing constraint for constants, and also theorems. What properties can you really derive and prove based on the axioms that are already declared? Not necessarily everything is provable, in which case they may just have to be assumed as axioms, right? Something that will also give you more details. And the other part for the formal specification in Rodent will be dynamic machines, meaning that the machine is going to evolve as it interacts with the user by invoking the events. So that will include variables, which definitely can change its value, and also invariants will be some property that we will expect to be provable to be true always. It should be established by the initialization events, and it should be also preserved as each event is executed. That's basically what an invariant really means. Literally, simply means a condition that should always be held. And we talk about events. You can think about events as just the the way like a communication channel between the machine and also outside world, like a user. And also the guards will determine whether or not an event is actually enabled for interaction or disabled for interaction. And also the actions, which will actually do the actual updates for each individual event. We'll talk about all these details later as we go for the case study. And we're going to talk about the notion about proof obligation associated with proving different things. So you can think about proof obligation are simply that if you want to prove the correctness of your system, you must discharge all the proof obligation. That's why they're called obligation. And the way you discharge them is by using proofs, right? That's really what it means. And there are two kinds of things that we may want to prove. One is about refinements. As we go through the refinements for the bridge controller, we'll give you the rules, okay, as we go there. But for now, just think about every time you do some refinements by introducing some extra detail into your model, you have to also prove the associated proof obligation related to the refinements. And the second thing you may want to prove is about system property. So these will be stated as invariants for the machine. You want to make sure those properties will be, number one, established by the initialization events, and number two, preserved by all the other events as we go, as we interact with the outside world. And finally, we want to make sure you can apply the inference rules. That's more technically about how you can conduct proofs on the paper. So you have to get used to the sequence calculus syntax, which I'll definitely go over as outlined in the textbook. And also know about the different rules. You can definitely create some data sheets or crib sheets as you actually go for study the lecture. All right. So these are the learning outcomes, and I would like to now move on to revisit one of the concepts that we spoke about earlier, which is called correct by construction. Before I go on and repeat some points and give you some additional insights, you may just want to think to yourself, what's really correct by construction based on what I learned in the introductory lecture. All right? Assuming that you thought about it, hopefully briefly, and let's now review about what a correct by construction is. And now we're going to put a little bit more new context into it, rather than just simply repeating what we said earlier. All right, so we know we should all agree this one to begin with. If you got some source code written in some programming language, could be C, manipulating pointers, or it can be Java, which got dozens of classes interacting with each other. In that case, reasoning about source code directly is too complicated to be feasible, right? For any realistic application. We really want to do one thing at a time, maybe one model or like a one artifact which is only concerned about certain properties you want to satisfy, only several at a time rather than all at one go, right? It's simply too complicated to be feasible. That's the number one point you want to remember. This is why there's such an existence of this course, because we want to make sure rather than going directly to assess or to prove or analyze something that's too big, you want to do construction one at a time, something much smaller. Right, so instead we want given the requirements document, so this is something I want to introduce from this week, which you also did a little bit exposure in your lab number 1 tutorial. Okay, so prior to implementation, you actually want to develop models rather than just a single one, rather than just a source code. Right? People used to say the only model of the most accurate model of your system development is the source code. To some extent, it might be true, but in many cases, it's simply not true, especially for verification purpose, right? And so prior to implementation, the final source code, you want to make sure you can develop models with increasing level of concreteness, meaning that starting from the most abstract and adding more and more details to make it more concrete until you get a model that's sufficiently close to the final code. That's something we want to do. It's called refinements, and that's also part of the title for this course. Right, so each model will formalize an external observer's perspective of the system. Right, so that's something I want to just annotate as we go for the bullet points. Remember this kind of a progression of the models over here. We are doing that progressively, right? Starting with the most abstract model, eventually we want to get maybe the nth model. That will be the most concrete. But for every one of them, you want to make sure you understand that for each model. So each model formalizes the public view of the system under construction. Meaning that you don't really want to show too many private things over here in the model. You want to focus more. Maybe in the final one, when you're actually getting more, getting closer to implementation, maybe you have to introduce maybe some private variables. We'll talk about it. But in the beginning phase, in the beginning portion of the model, you want to make sure you focus more on the public view, like how the external observer is going to interact with your system. So that's why I said the bullet point. It should be how the external user perceive your system. So that should be the goal for the most of the models, right? That's something I want to say first. And then models are sorted with increasing levels of accuracy with respect to the system, meaning that we start with this one may not be exactly accurate, but it does contain some useful information that's part of the truth. Well, it's part of the complete details, but you don't give all the details in a single model, right? So it will become more and more accurate. So the final one hopefully will be accurate enough so that you can directly write some code based on the final model, right? That's something we said before in the introductory lecture. So for that point, I wouldn't repeat, right? You can definitely refer to that part just to complement what we are saying over here. I'll only write down something that's new to you. Right, the first model, even though it's the most abstract, it can already be proof and satisfying some requirements. Remember, we are given some requirements document. So that's something I would like to draw your attention to this time, right? Think about what should really go side by side with your model development process. There will be a document over here called requirements documents, right? It's called RD. Requirements documents. Requirements documents. And we'll talk about a little bit later about the in principle you can divide your requirements document into two kinds of description. So one is about E description, and the other one is the R description. And I got some slide later to talk about each one of them, so we get there when we talk. We'll talk about detail when we get there. But these will be the two kinds of descriptions you should be able to find in the requirements documents. So all your model development should be based on the requirements document. And as I said, for this course, you will be given these documents over here. So your job is to say, having seen the natural language version of the description, how can we formulate them, or how can we formalize them into individual model, right? That's something you want to keep in mind. And also, it's really important to say for M0 over here, definitely the most abstract for sure. But we can expect to encode and prove some. Right? Some over here is really important as opposed to all. We definitely don't want to put everything or to prove everything in a single model. Some constraints and properties from, okay, let me write better, FRON, the requirements documents. Right, so here the keyword is only some, and from the requirements document. So this will be the authoritative reference you always should really refer to whenever you are building your model. That's something I will do when we talk about different models for the bridge controller. I will tell you which requirements that we are referring to, which E description or which R description. All right, and it will be true for all the models over here. Maybe for N0 we only talk about some E description and some R description, and maybe for MI, so this will be maybe some intermediate model, we'll talk about some additional ones over here, right? Sometimes we may have to overlap to really give more elaborate details, and sometimes we may just talk about different parts of the requirements document. So there's no fixed rule about how you should really mix the requirements document, but the principle is you don't really try to handle the entire requirements document in a single model. In that case, you're basically trying to reason about directly into the source code, which is, we said is not feasible. All right, and starting from the second model, each model is analyzed and proved correct relative to criteria. And something I can also say in addition to what you heard in the introductory lecture. Number one, there will be some requirements, especially our description we want to prove, right? So for example, let's now talk about, in general, let's say we got the earlier model MI and then the later model MJ, right? I think the error over here is not exactly correct. I think I really meant to say there should be no ... So we got exactly one arrow in between. Okay, let me just emphasize that. So from MI to MJ. Okay, so they are adjacent to each other, right? That would be the right way to put it. Okay, so you can think about what we're having over here is when MJ over here refines NI, right? Several things we want to say. Number one, over here, let me just do this a little bit thinner. Okay, number one, MJ refines MI. Refines NI. Or you can say MI is refined by MJ, right? And typically, when you say refinements, that means you actually got by introducing some extra artifacts, either state variables, like extra variables. I'll talk about what a state is in the next slides. State variables, you're just adding more variables in the refinement machine, and or some state variables and also events. So by adding some extra stuff into NJ, you want to make sure those kind of extra stuff would not make the behavior of NJ not consistent with MI. So that's basically the notion about refinement proof obligation, right? So what we want to prove conceptually, right? So let me just write down the conceptual idea. So if you really consider these two machines over here, so there will be some proof obligation of refinements. And informally, it's just going to make sure NJ behaves consistently with respect to MI. Right? That's all we need to know just for now. But later on, when we see the formal proof obligation expressed in mathematics, we'll see more precisely, right? But just for now. But what you should know is, in a single refinement, we may just introduce some extra state variables and also events. Since we introduce some extra stuff, so we want to make sure, number one, the proof obligation for the refinements can really be discharged so that MJ is really behaving consistently with its predecessor. And similarly, we want to make sure all the model behaves consistently with its like an ancestor or like a predecessor. And also MI should also behave consistently with maybe I minus 1 and etc. Right? So that'd be the first thing we want to make sure that's satisfiable, which is about refinements. And the second one is maybe some requirements. So again, every model is only supposed to address some requirements, not all, right? So these are the two things I just mentioned over here, right? All right, and then so here's some extra state variables and also events. That's what we typically do for refinements. And the last model over here, as we also mentioned in the introductory lecture, the last model over here, of course, n over here, how large it is, there's no fixed rule about n should be like a greater than or equal to 10 or something. No. So I would say it depends on the case study you're conducting. In the case of the bridge controller, n will just be equal to 3. Okay, in case. Okay, I just say for example, n is equal to 3 for bridge controller. Bridge controller. Meaning that we're going to get M0, the initial model, and then we go to M1. M1 will be the refinement for M0. And then we go to M2. M2 will be the refinement for M1. And then we go to M3, the final model, which will be the refinements of M2. How many refinements do we get? 1, 2, and 3. Right? So that'll be the idea for the bridge controller. But in general, how large n is really depends on the case study you're trying to formalize. And the last model will be correct by construction because we make sure for every model we prove that it is consistent with the earlier one, and also we make sure it satisfies certain property, and presumably eventually we can prove all the properties, and we distribute the proof of all the property into different models, right? So that we can make sure the final one, once we prove its refinement with respect to the earlier model, and also we prove that it satisfies certain additional properties, that we can conclude it will be correct by construction with respect to the requirements documents, right? That will be the idea, right? So we're just adding more information to what you learned in the introductory lecture, by requirements documents, and a little bit more precise about what refinement is, but we'll see even more precisely mathematically later.